Welcome to this explainer on aircraft fire protection and warning systems. We're going way past the basics today to look at the precise mechanisms and redundant layers that prevent a localized spark from escalating into a catastrophic event at 30,000 feet. We are essentially tearing down the anatomy of a safety net that simply has to work flawlessly every single time.
We are pulling our insights straight from the Amte 241 engineering curriculum, specifically lessons 15 through 20. And let me tell you, this coursework doesn't just skim the surface. It meticulously breaks down the physics of fire detection, the chemistry of suppression, the stringent testing protocols, and the absolute laws governing airworthiness. It's the exact rigorous knowledge base used to train the engineers and mechanics who keep these massive machines safely up in the sky.
Now here's a kind of fascinating contrast for you right off the bat. Our absolute most powerful fire killer, it's strictly a ground-based defense. You might assume a multi-million-dollar aircraft would carry the heaviest, most potent suppression agent possible, right? Well, voluminous foam systems are just entirely impractical for weight-sensitive flight operations. Foam requires massive amounts of water and really bulky generating equipment. In the air, every single ounce matters. So aircraft rely on highly concentrated, lightweight gaseous agents like halon for onboard suppression, leaving the heavy lifting of chemical foam strictly to the ground crews.
So here is our flight plan for this explainer. First, defending against aviation fires. Second, the aircraft's internal nervous system. Third, inspection and system testing. And finally, the strict rulebook of airworthiness.
Let's start with Part 1, defending against aviation fires, specifically looking at foam protection systems.
Picture this. When you're dealing with highly volatile aviation fuel on a ramp or a runway, regular water just isn't going to cut it. In fact, water can actually spread a fuel fire. Instead, firefighting foam is the ultimate solution for Class B flammable liquid hazards. Mechanically, it works by deploying this dense aqueous blanket that rapidly spreads right over the surface of pooled fuel. And doing this accomplishes three absolutely crucial things. It smothers the fire by separating the fuel from the oxygen, it dramatically cools the surrounding area, and, perhaps most importantly, it suppresses highly explosive fuel vapors from rising up and reigniting. It's the absolute primary tool for rescue and firefighting operations on the ground.
Okay, moving from the ground to the sky, let's jump into Part 2, the aircraft's nervous system, focusing on system monitoring and indication.
Once we're in the air, understanding the absolute distinction between a simple indication and a critical warning is literally a matter of life and death. An indication is essentially just a status update. It's a visual cue on a screen saying a system is operating normally, or maybe a minor anomaly popped up that just needs to be monitored. But a warning dictates that there is an immediate, catastrophic threat right now, like a fire in engine number 2. And to ensure this is never, ever missed, aircraft rely on human factors engineering. Warnings are literally impossible to ignore. They trigger blaring red master warning lights, specific inescapable oral tones like a loud fire bell, and immediate prompts on the crew's central displays, demanding urgent, decisive action.
But wait, how do we actually know that highly complex electronic nervous system is totally healthy? How do we know those warnings will actually trigger when we need them to? Well, that's where BITE comes in, which stands for Built-in Test Equipment. Think of it like the aircraft diagnosing its own nerve endings. When a pilot or mechanic initiates a BITE check during pre-flight, the system shoots low-voltage electrical currents through the entire detection loop. It simulates faults to verify absolute continuity across every single sensor, wire, and indicator lamp. And it does all this without actually discharging the highly pressurized fire extinguisher bottles. It detects microscopic hidden faults before the aircraft is even cleared to leave the runway.
Now, when a fire is actually detected, the warning system doesn't just ring a bell and leave it up to the pilots to figure out the rest. No, it triggers a precise, automated cascade of events. Usually, a pilot will pull an illuminated fire handle, kind of known as a T-handle, in the cockpit. The physical action of pulling this handle initiates an immediate interface with multiple critical systems. In a fraction of a second, it forcefully shuts off the fuel valves feeding the burning engine, it trips the generator off the line to isolate electrical power and prevent subsequent sparks, it shuts off the hydraulic fluid supply, and it closes the bleed air valves for the environmental control systems. That last one ensures that toxic smoke is never pumped into the passenger cabin. It's essentially a perfectly orchestrated quarantine of the hazard, managed seamlessly through the centralized alerting system.
Which brings us to Part 3, inspection and system testing, where we verify these defenses.
Because honestly, none of these sophisticated, interconnected systems matter at all if they aren't properly maintained. Routine testing and inspection involve incredibly strict adherence to documentation and regulatory requirements. This isn't just about ticking a few boxes. It's about actively hunting down microscopic signs of degradation. Mechanics are looking for specific, physical vulnerabilities. We're talking about things like chafed sensor wires that could trigger a false alarm, thermal switches that have lost their calibration over thousands of flight hours, or even a slight pressure loss in the localized fire extinguisher bottles. When an inspection reveals any of these findings, executing immediate by-the-book corrective actions is the only path forward. Every repaired wire and verified pressure gauge directly guarantees the integrity of the aircraft's defense systems.
And that leads us right into our final section, the Rulebook of Airworthiness, looking at fire protection regulation.
Look, I know navigating aviation law can feel like a bit of an alphabet soup, but the global mandate for safety is remarkably unified. Whether it's the FAA in the United States governing transport category aircraft under Part 25, Europe's EASA enforcing their CS-25 requirements, the Civil Aviation Authority of the Philippines strictly utilizing PCAR Part 3, or the overarching international baseline set by ICAO's Annex 8, the end goal is exactly the same. These regulations aren't just polite guidelines. They are the absolute, non-negotiable legal foundation for how every single fire safety system is designed, tested, and maintained globally.
Before a brand new aircraft model is ever legally allowed to carry a single passenger, its internal fire systems have to survive an exhaustive, multi-step certification gauntlet. It starts with rigorous design approval and testing on paper and in the lab. Then, it moves to intense real-world ground and flight test validation. After that comes the heaviest lift. Engineers must compile thousands of pages of compliance demonstration reports. This places an immense burden of proof on the manufacturer to empirically prove the system works flawlessly under every conceivable failure scenario. Only after surviving all of this is the aircraft awarded a type certificate proving beyond a shadow of a doubt that it is legally safe to fly.
And here's the kicker. Regulators don't just want the system to sort of work in a cozy, controlled laboratory setting. Oh no, they demand proven accuracy and speed under the most hostile environmental pressures imaginable. The certification process aggressively tests for flawless fire detection accuracy. That means absolutely zero false alarms that could prompt an unnecessary emergency landing, but also an absolute guarantee of zero missed fires. Furthermore, the containment and suppression agents have to deploy in milliseconds and prove highly effective even when the aircraft is subjected to the brutal realities of flight. We're talking sub-zero temperatures at 40,000 feet, extreme structural vibrations, and rapidly fluctuating cabin pressures.
So, the aircraft achieves certification. Great, but keeping it certified, that is a massive, highly regulated undertaking. Operators have to strictly adhere to a vast library of living compliance documents. Mechanics rely on the aircraft maintenance manual and the component maintenance manual to execute the physical work and the illustrated parts catalog to source the exact certified hardware. But crucially, they really have to differentiate between manufacturer guidance and absolute law. While a service bulletin might offer a highly recommended safety upgrade from the manufacturer, an Airworthiness Directive, or AD, is a legally enforced mandatory mandate from regulators to immediately address a known safety threat. And if you fail to comply with an AD, that aircraft is instantly grounded. Period.
So I'm going to leave you with this question to think about. This system is certified safe today, but through continued airworthiness, who ensures it's safe tomorrow? Building a safe aircraft is a technological and engineering marvel, one that is certified safe on day one. But through periodic inspections, rigid configuration control, and incredibly strict maintenance record keeping, it's this concept of continued airworthiness that ensures it remains safe every single day after. It's a relentless, unwavering human commitment to zero tolerance for error. Thanks for joining me on this explainer, and I hope you walk away with a much deeper appreciation for the true anatomy of aircraft fire safety.